Hello and welcome everybody to a new seminar in the CONT seminar series. Today I have the privilege of introducing our online speaker, Milena Rangelov. Dr. Rangelov is the Vice President of Research at VitalMetrics. Her research interests include life cycle assessment, sustainability of transportation infrastructure, and low carbon materials. She received her bachelor's and master's degrees from the University of Belgrade and her doctorate degree from Washington State University, all in civil engineering. Please help me welcome Milena. I kindly request from you to keep your questions till the end, as Dr. Rangelov will have 35 minutes for presentation and 10 minutes for questions and answers. So the stage is yours, Dr. Milena. You can go ahead.
Thank you so much, and thank you for having me. I'm very excited about this seminar, and I hope you guys learned something interesting and useful. Sustainability is definitely a hot topic in all these different areas, and infrastructure is no exception. So I will share quite a bit of work that I have done during my time working for Federal Highway Administration and under Sustainable Pavements program. Right now, I'm with VitalMetrics, which is environmental consultancy, and you will see implementation of the tool lifecycle assessment for different types of pavement projects and pavement materials. Here is my list of acronyms. As you know, when we talk about sustainability, acronyms are abundant, but I will try my best to cover each and every one of them as we go so you can follow comfortably. So, as you know, pavements are the part of infrastructure transportation system. And usually when we talk about transportation, we talk about very high greenhouse gas emissions. That's typical. And on the left-hand side, you can see this chart from EPA that is an inventory of the entire US industry and how each sector contributes to greenhouse gas emissions. And you can see here, this pink pie part of the chart is transportation, often characterized by largest CO2 emissions from all sectors. However, that's not the whole story. These are only tailpipe emissions associated with vehicles, whereas pavement infrastructure and our built infrastructure, which is essential, you can't run car without pavements, is kind of mixed between these different categories. So here we have on the right-hand side, we have pavement life cycle stages from raw material manufacturing, mixed design and production, construction, use phase, maintenance and rehabilitation, and end of life. And in each one of these phases, we have a little bit of impacts of industry, which is blue, meaning our material production. We have electricity that's used to produce pretty much anything, as well as a little bit of transportation, which is hauling and shipping. All of this is to say that the question, what are the environmental impacts of transportation, is a complex question, and it's hard to delineate this, but pavements should definitely be considered as the essential part of transportation systems when we're talking about GHG mitigation. Often when we talk about sustainability and pavement sustainability specifically, and I worked a lot with different state DOTs, and we asked them, what are you doing in terms of sustainability? They say, oh, we're good, we're recycling. And often there is that idea that recycling is sustainability. And we usually call these practices feel goods because recycling makes sense, right? You feel good when you throw your soda can in recycling bin. However, we don't really know the benefit or lack thereof of any practice until we do the analysis and we calculate quantitative metrics. And as engineers, we are pretty good at that. Here I'm listing some common practices, such as incorporation of waste materials in our pavements. There is initiative to incorporate plastics, ground tire rubber, other types of recycled materials, increasing durability. Durability is fine, right? Often people equate durability and sustainability. using local materials, all these best practices. But our premise has become a lot more along the lines of you cannot improve what you don't measure. So we cannot claim that any practice is sustainable outside of the context and outside of quantitative metrics. So when I'm talking about quantitative metrics, we have different metrics for all pillars of the triple bottom line, meaning triple bottom line is sustainability represented as the balance of economic, environmental, and social components. And here in the center, you can see we have this little road and this little landscape. People often ask us, what about performance? And performance is a must. It doesn't mean that we should just try to reduce greenhouse gases at the detriment of performance. That's where life cycle thinking comes into play. So all components of performance are baked into sustainability. That's kind of one little preface. For economic aspect of sustainability, we have the method called life cycle cost analysis. I believe in your pavement design classes or other types of classes, you got familiar with this method. For environmental, the method of choice is life cycle assessment. That will be the focus of my presentation. And then for social impacts, we have sustainability rating systems that address all three components, including social, and there is new emerging method called social LCA. I'm not going to spend a lot of time talking about that. We can definitely engage in questions afterward on social LCA. That's new and emerging method, and Sustainable Pavements program in these last couple of years has done major advancements on LCA. There is increasing interest in greenhouse gas mitigation. So I will be focusing on LCA and environmental portion of sustainability. Life cycle assessment is a technique to quantify environmental impacts of products and processes throughout their life cycle. So in this slide, you can see simplified life cycle of what could be pretty much any type of product. We are starting with raw material acquisition. We have then material processing, manufacturing, use phase, and end of life phase. We call it life cycle, even though here it's stretched and it looks more like a line. But with different types of reuse, remanufacturing, recycling practices, we are trying to close this circle so that life cycle is circular indeed. What's typical for any type of production is that we have inputs in terms of materials and energy, and we have outputs in terms of waste and emissions, because when we're producing our products, we're not only producing these products, we are also releasing some chemicals or some wastes into the environment, into soil, water, air. And we also have these transportation steps in between. These are these little trucks. So pretty much whatever we do, these are some of the common denominators. So when we are doing life cycle assessment, we are doing detailed environmental accounting of all inputs that are going into our system and all outputs that are coming outside of our system. And we are converting those outputs into environmental impacts. One of those environmental impacts is global warming potential, but there are many others, but global warming potential is the most famous one for sure. In this slide, I'm showing our paper. You can see the info about this paper at the bottom. And if you do any type of sustainability related study, this paper is really good for the intro. Just a little pitch here, FYI. It's an interesting one because in this study, we worked closely with state DOTs and trying to figure out their process of decision making and where LCA fits the best. As you can imagine, LCA is very versatile, but you need to know exactly what answer you're trying to do and what decisions you are trying to influence. So blue portion of this graph shows the stages on how state DOTs are making decisions, starting from a long-range transportation plan, where they just set the general goals for their infrastructure, programming, where they have fiscally constrained plans of 4 years or so. And then we go into project development. If you are an engineer, you do pavement design, this is kind of where the most of it happens. Then we have bidding, typical design, bid, build. There could be other types of project delivery. This is just the common one. And we have construction phase. Then this is a cycle. this is not the end, but rather just the beginning, because then this is when our asset is used as intended, and we are, have traffic operations, maintenance, preservation, other activities, depending on how our asset performs. Asset and performance management, all of this is in the use phase, and the data from these stages is informing these other broader stages. So that's what state duties are doing. And then we have different types of LCA. I'm not going to spend like too much time on each and every one of them, but LCA can support pavement design, which I'm going to show you today, and the tool that can be used to do so. Use of EPDs, environmental product declarations, very useful in bidding. In fact, legislated in a number of places. And then in construction phase, that's a potent phase where we can collect all sorts of data and improve our analysis in the future. If you want to learn more, I definitely suggest you read a paper, because it's packed with all sorts of different types of information. So this was more like theoretical concepts. Now I will go into examples. As you know, for our infrastructure, we have concrete pavements, we have asphalt pavements. And when I was in FHWA, it was very important to balance the interest of the two industries. That's kind of what's propelling the innovation. And I will present one example from asphalt side and the other example from the concrete side, so you can see how LCA can be implemented. This case study that I'm going to show is the case study of Puerto Rico, which is the Caribbean island, was recently hit by a hurricane and has some resiliency related concerns. But this problem that we were working on mitigating was the problem of waste tires. Puerto Rico is grappling with excess waste tires, and the problem is in some areas they present fire hazard. They also present health hazard because they are retaining the water and helping propagation of mosquitoes and mosquito-borne diseases, which are conducive of epidemics. And as you know, Puerto Rico lives off of tourism, so epidemics can create a havoc on an island. Obviously, that has broader economic implications. And then we were investigating what are the alternatives to the current practice, which is shipping them to other countries, such as Costa Rica, India, China, Brazil, to burn these tires in cement kilns. They were interested in seeing how tires can be used locally, and one idea was to use them as asphalt modifier or asphalt additive. This was a collaborative effort between FHWA, EPA, PRHTA, which is Puerto Rico DOT, and their public officials. They were interested in investigating the policy to require all pavements to contain certain percentage of ground tire rubber. And we also had academics from NCAT, National Center for Asphalt Technology, as well as University of Puerto Rico at Maya West. So we had like a very broad team to investigate this problem from multiple perspectives. So as I said, proposed solution for local usage was the use of ground tire rubber in pavements. We have seen this practice being implemented a lot in Arizona, California, New Jersey, Nevada. So there are many states that already have experience with GTR. And there are potential performance benefits. GTR is elastic, so it can help with rotting resistance. In some cases, you can have improved safety, less noise. So there are many benefits of this practice that can be achieved. But the question, of course, is what are the environmental repercussions and trade-offs? Can you optimize the benefits? How can this practice be implemented in an informed fashion? So in this study, I'm showing you here the pavement product system that we have investigated. And we have compared the conventional pavement section between GTR modified section. All these sections were built in Puerto Rico as pilot test sections in 2013. And they have been performing well so far, a very similar performance, or the performance of GTR even being slightly better. So here I'm showing how product system is formulated. We have components such as asphalt binder, aggregate, admixtures. All of them are shipped to the mixing facility where we perform the mixing. Mix is then shipped to the construction site where it's compacted. Use phase is empty, and I'll talk about why in just a second. And lastly, we have end-of-life treatment. And then our GTR modified section is pretty much the same, but we have a few additional elements. One of them obviously is GTR that is obtained by shredding, granulation, and cleaning of waste tires. We have output of waste and steel, and then GTR goes under binder modification with asphalt binder, and then all other processes are the same. These sections were only 2 inches thick. That's why I'm not considering any maintenance here in the use phase. And then there are other impacts of pavement vehicle interaction. We can talk more about that later. That was omitted for this one for some reasons. And again, if anybody has a question, I can elaborate more on that. But we assume that because these sections are more like overlays, that at the end of the life, they would just be removed, because in Puerto Rico, typical maintenance cycle is 2-inch mill and fill. So basically we just remove the section and move on. In this slide, I'm showing the comparison between control section in navy blue, and then this red pink is GTR modified section. We have 5 environmental impact categories. First one is acidification, which is the formation of acidic rains. Eutrophication, which is extensive nutrient supplies to water, so water pollution with excess nutrients. Global warming potential, ozone depletion potential, and smog creation potential. These should be quite self-explanatory. These mixes are normalized by the annual US production. So therefore, we can not only compare the 2 sections, but we can also gauge which environmental impact categories are more impactful than the others. So first thing, we can see the difference between dark blue and red bars is that GTR section has slightly higher impacts, 7% up to 12%, depending on the specific impact category. That's one thing. And then second thing is that we have the most significant impacts are smog creation potential because of fossil fuels, GWP, and acidification. Eutrophication is typically not very high relative to the whole industry because it's most typical in agriculture. And then ozone depletion also typically function of different types of refrigerants and freons, which we don't use a lot in pavement industry. Here we are breaking down the results for cradle-to-grave scope for these 2 sections, and we can see the difference between the 2. So first of all, we have asphalt binder. In GTR modified section, we have slightly higher binder content because GTR modified binder has increased viscosity, and it's used with open graded aggregate gradation, so we need a little more binder to achieve the same result. But that's not all. With the binder, we also have binder modification process as well as GTR processing. All of that comprises our modified binder. As you can see, the impacts of that binder are quite a bit higher comparing to HMA. Next one is aggregates. Aggregates is the white category right here, and it's pretty okay, relatively low impacts. Next one would be transportation. The hatched one, that shows us if our ingredients are local or not. And here in this case, we have asphalt binder being imported from Colombia, whereas aggregates are local, and of course tires are local, as we mentioned. Mixing is another important chunk and a little higher for GTR mixes because it requires higher temperature. And then we can see construction and end-of-life treatment, they comprise around 20% of impact, so the bulk of it is materials, is the initial construction. So GTR impacts are higher. However, these impacts can be compensated for if section presents improved performance. So how much better we need GTR section to perform so that it breaks even, quote unquote, with conventional section in terms of environmental impacts. So this slide will give you the results. If we assume the 10-year performance of control section, which is the baseline, we see that GTR needs to perform 20% longer satisfactory, so that they break even and they can be considered equal. So those higher impacts up front can be compensated for by extended performance. Are we going to have that? I don't know, and that's a good question. That's where we collaborate with our colleagues that do asphalt material science. So we definitely need performance data to inform this LCA. This is just hypothetical. So it's like, hey, if GTR section underperforms, it's not going to be more sustainable than the conventional, but if it performs, let's say for 12 years or more, it will win in terms of environmental impacts. Here I'm showing the system level analysis, and this is a very interesting one because it was directly used to inform the policy. Here we have the number of waste tires in Puerto Rico, 3.7 million. That's a lot of tires. And we have investigated these business as usual scenarios on the left-hand side, where all of the tires are processed as tire-derived fuel or TDF. And Puerto Rico paving is hot mix asphalt conventional one without any changes. However, if policy is introduced, we could be able to repurpose portion of these tires into asphalt modifier. We have done extensive analysis on how much that could be. And we have discovered that if you stretch all Puerto Rico systems, you can only eat up around 11% of tires. Keep in mind, this is extremely optimistic scenario. However, if we do that, we can achieve 75% of Puerto Rico paving with GTR, which is what policy was investigating, and 25% of paving will remain HMA. So in that case, we would also have some tire-derived fuel because pavements cannot eat up the entirety of tires that are available. There are just too many. So in this slide, I'm comparing business as usual scenarios to modified scenarios. And there is a difference here if tire-derived fuel replaces an intensive fuel combination or greener fuel combination, depending on what your cement kiln is using. So in this, let me see, in this first scenario, we actually have modified option. So if your kiln is using coal and petroleum coke, more intensive fuel combination, it makes sense to push tires into the kiln and keep to your business as usual. However, if you have more of state-of-the-art kiln, then your business as usual is actually better than is actually worse, sorry, or equal, like the modified scenario. And in that case, using these tires not to replace greener fuel combinations, but rather in pavements makes more sense. This is a loaded slide, so if there is a need, I can explain more later. Just want to keep to the schedule. So this is my asphalt example, and now I'm gonna switch gears a little bit and talk about my concrete example. So in this study, the Sustainable Pavements Program, which I was a part of, and Mobile Concrete Technology Center were collaborating. Mobile Concrete Technology Center is also known as Concrete Trailer. You can see it here. It is actually mobile concrete lab that travels all across the country and performs the deployment of various pavement technologies. We have asphalt one, we have concrete one, so we're kind of covering all of the bases. So in this study, we wanted to evaluate the state of practice of paving concrete because they have a lot of data out there, and to identify if there are opportunities for improvement from the sustainability standpoint as well as durability standpoint, which is what they are advocating for. So I'm showing you the data that they have collected between 2011 and 2019. They had 28 main lane paving projects. They had more projects, but some of them were research projects or other specialty mixes. This is your bread and butter type of concrete for paving. And as you can see here, we have sections in projects all across the US, including Hawaii. Remember, Hawaii is going to be important for some of the next references. By the way, my first question was, how did you get trailer to Hawaii? But trailer didn't travel across the seas to Hawaii. They just shipped the equipment. Anyways, if you look at that report, they have some beautiful sunsets and some amazing concrete pavements. So in this slide, I'm showing mixture statistics based on what MCTC has collected. So in this first graph, graph A, red portion shows cementitious contents, total cementitious contents, and we can see these lines that are kind of bracketing typical slip for paving specifications. What we have seen very early on from this data set is that we have our total cementitious content is a little bit on a higher end of what is typically specified. So we are using a little more powder than we probably should. On the graph B is showing the paste content. And if you are familiar with performance engineered concrete mixtures, this new AASHTO standard PP84 is specifying that 25% content is optimal, and that for paving concrete, we should not be above 25% of paste because it can have detrimental durability effects. As you can see here, most of our mixes indeed have paste content above 25. In terms of SCM usage, we have pretty much most mixes are using some SCMs, and most common replacement ratios are between 20 and 30%. There was only one mix without SCMs, and that is Hawaii mix. They don't have SCMs available. Most mixes are binary, meaning they use cement and one type of SCM. We also have some ternary, and again, one plain mix from Hawaii. In terms of different SCM types, most mixes are using type F fly ash, some are using type C as well as slag. In one mix, I believe it was Nevada, they used natural pozzolan because that was locally available. And then water to cement ratios are ranging between 0.35 and 0.5. And this is important for durability consideration. I could also add that this is kind of a broader range. Probably some improvements are possible in that regard. So main takeaways is that we have relatively high cementitious contents as well as paste contents, typically due to some of the prescriptive concrete specifications. When we looked into other data that they have collected, these would be compressive strengths on different test dates. And here on the left-hand side, you can see 7, 28, and 56 days compressive strength. And then the shaded area right here represents typical 28-day design requirements. We can see that most of our mixes achieve that 28-day compressive strength requirements already on day 7, and then on 28 days, compressive strengths are quite a bit higher than what is specified. There are several reasons for that. One is that contractors are typically penalized if compressive strength doesn't pass, so they do tend to add more cement to their mixes just to make sure that they don't have any penalties. However, that is increasing the cost of the mix as well as creating some durability concerns. On the right-hand side is surface resistivity. That's not analyzed in this study per se, but we have a new study that is coming up where we analyze surface resistivity and sustainability correlations in detail. So once we analyze mixes in this way, we have done LCA on them. This slide is showing weird. I apologize. Some letters are in new line. Sorry about that. So we have very similar to asphalt. Here we have aggregate production, cement, supplementary cementitious materials, admixtures, and water, all shipped to concrete mixing plant. We work with state DOTs to kind of assess their transportation distances for all materials, and we created cradle-to-gate concrete LCA. Obviously, this is not cradle-to-grave, but because we worked with MCTC and they gave us some durability data and durability indications, we are confident that our recommendations would not be detrimental from like full life cycle standpoint. So let's see some trends. This first graph on the left-hand side is showing the correlation between cement content and GWP, global warming potential, in kilograms of CO2 equivalent. We can see very strong linear correlation between the two. And then these mixes are summarized in different colors based on the mixture type. So there are differences in different clusters of the mix, if you will, based on the mix types. However, regardless, across the board, we have very prominent positive linear correlation between cement and GWP. Higher cement, more GWP, period. On the right-hand side, we can see correlation between cement paste and GWP. It is still positive correlation, but it's not as prominently linear because not all pastes are created the same. So 17 mixes that didn't have paste content below recommended 25%. We have done redesign and recommended some improvements to save in terms of environmental impacts. But before we go there, I can show you process contributions for all of these mixes. Here, these names of the mixes are tied to the state. It's just one mix per state. It doesn't mean state is doing good or bad. It's only used here as a data designation. However, one big takeaway from this graph is that you can see how big portion of these bars is the gray color. So that's cement. Cement, based on this research, has contribution between 73 and 93%. And as such, cement is the highest contributor to GWP of concrete. So if we want to make concrete more green, we need to figure out the ways to reduce cement content, as well as figure out the ways to make cement produced in a more environmentally friendly fashion. Other processes that are noteworthy are transportation. It all depends on where your constituents are coming from, if you have local materials or you need to ship them, as well as slag processing is another component. In this slide, I'm showing business as usual baseline mix as kind of the outside pentagon. And then these are improvements in 5 environmental impact categories when we reduce the paste by making it matching recommended 25%. And by the way, to do that, you need to optimize your aggregate gradation, which is usually straightforward to do. And we can see here that not only our GWP improves, and we can achieve up to 16% reduction just by doing that, we also see that all other environmental impact categories are improving at the same time. So we are not having any trade-offs, plus the cost is going to become lower, and durability is going to become less of an issue. So this is a clear win-win situation and is a readily available technology that can be leveraged immediately. We have published TRB paper on this. So if you're really interested to learn more, you can contact me and I can share the paper with you. One last thing I want to mention are EPDs, or environmental product declarations. Why our interest has been on EPDs recently is that there are many green public purchasing initiatives all across the United States. We have seen, first of all, California was a very proactive state that legislated by Clean Act in 2017, in fact, is when it became official. And then Colorado last year and Oregon this year. So what does this mean? It means that from now on in these states for publicly purchased materials of choice, producers will have to submit EPDs, environmental product declarations, that are based on LCA. And then in some cases, future acceptance of these products will be contingent on global warming potential as reported on their EPD. So this changes how we are purchasing our products. And then in infrastructure, this is very important because that's typically public purchasing. So there is a lot of effort. We also had Buy Clean on federal level introduced just a couple of weeks ago in early September. So there is a lot of movement in this space. Very interesting topic indeed. And as you can see here, some other states are considering this. We are not able to track them very well. I do believe Illinois now, speaking of that, is considering this initiative. We have another research project with a colleague that will kind of try to collect this data and update this chart a little more recently, so we know when these acts are legislated, but we don't know when they are considered. Anyways, what are EPDs? EPDs are environmental labels that communicate impacts of materials or products based on standardized LCA. So this is a mini LCA for a product. We're usually comparing them to nutritional labels you can see on your food products that enable you to make more informed choices about what you're going to eat. So EPDs are similar. They inform us on environmental impacts and therefore help us choose greener products. So they follow industry standards described in PCR or product category rules. So they're highly standardized form of LCA. You have seen my graphs related to asphalt and concrete product system. So what I did for concrete is very much similar to the way you would develop your EPD. Here I'm showing asphalt mixture EPD, how it can consist of aggregate, binder, and admixtures, EPDs as kind of mini building blocks. And then asphalt mixture EPD can be featured in pavement LCA and used as a data source as kind of little piece of the puzzle and help us create this whole pavement LCA product system. Very important item. So here is another paper that we have developed, and it's about EPD and EPD uses. EPDs started as communication tool, and they are now being used as procurement aid. But of course, we also want to see them used as data sources, and that requires higher and higher level of standardization. Elements of pavement LCA, this is something that FHWA has been working on a lot. We have also developed LCA benchmarking tool, LCA PAVE, which is completely free, uses EPDs as a data source. So if you are developing master's thesis or any other project and you need to run pavement LCA based on the latest industry standards, you don't need to pay a dime. You can use this tool. And also, if you have any material EPDs, you can include them as the data sources. More information is available here on this website. And I also want to say that FHWA website on sustainable pavements, let me just go back, fhwa.gov/sustainable pavements. It has many more resources that are going to be very useful. So with that, I hope I didn't run over the designated time, or at least not much. I would like to thank you. Here is my contact info if you are interested in staying in touch. I also use LinkedIn pretty much every day, so feel free to add me there. And with that, I would like to open up for any questions you might have.
Thank you for the very nice presentation, Milena. Actually, we're exactly on time. So we have a good 10 minutes for questions. So first of all, first I will start with people in the classroom, and then maybe we can go to see if you have questions also. Any questions in here? Okay, we have a question from Lara. You can go ahead.
Hi, Milena. Thanks for the presentation. I wanted to ask about, sorry, a very technical question, but I don't have the background. How do you actually quantify the paste content, and how is it so different from the cement content?
Yes. Okay. So the concrete paste consists of cement, supplementary cementitious materials, and water. Admixtures, we may argue, are very small volume-based contribution. So those components are your concrete cement paste. So basically everything that's not air and that's not aggregate is your paste. And then having optimized aggregate gradation will change the need for paste. And obviously aggregate is cheaper component and it's more structurally sound than the paste. So you are trying, when you're kind of designing concrete mix, you're trying to have a really nice and compact aggregate skeleton and just use enough paste to kind of fill in all the gaps and have some air voids, etc. So if you create better packing of the aggregate, you can get away with smaller paste content, and you won't have any of these durability issues such as shrinkage cracking, thermal cracking, freeze-thaw resistance. All is going to be better, all of that, because paste is what is kind of causing durability issues. So the reasons why paste is different than just cement is that, as you could see, and let me go back a few slides. I hope I don't make you very dizzy. We have all of these SCMs included, plus the water. So we, not every paste is equal. Let's say Hawaii mix, because it's plain, it only has cement and water. However, mixes in other states can have any one of these, let's say most likely type F fly ash or type C fly ash or slag. And because of that, paste quality is not the same. Also, when we're speaking about environmental impact, cement is the most intensive, whereas these other things such as fly ash and slag are industrial byproducts, so they have much lower impacts than cement. So fly ash usually you can incorporate directly in the mix without any processing. Slag needs to be ground, but it's definitely much less intensive than producing cement from scratch.
I see. Thank you.
Okay.
Excellent.
Any more questions? Maybe Larry could go.
Hello, thank you for the presentation. I was wondering if you can give us some details about the social advance, like what are the important inputs and outputs of the environment?
Very good. I like that question, and I think this is a very important up and coming area of work. And how it pertains to pavements, I'll be honest, we don't know yet, so we haven't figured that out. However, this type of research has been, or research and development, if you will, has been very prominent in the space of consumers products, such as say electronics. So for instance, if you buy a cell phone, you would like to know if like your battery is, you know, produced from like lithium from Congo, where you have child labor, all these crazy things happening, forced labor, all of these other issues. For pavement products, we are kind of lucky in that regard because most of our components are local, so we don't have the same concerns. So social LCA is very similar like environmental LCA, in a sense that you are trying to cover life cycle. You are trying to also like create goal and scope and like, why are you doing the analysis? The differences come in terms of data, and also impacts are categorized based on the stakeholders. So one stakeholder could be local community, one stakeholder could be the workers, one stakeholder could be consumers. So you are categorizing these impacts accordingly. And let's say for worker, impacts would be living wage. Like let's say workers have minimum wage, but can they live off of that minimum wage? Do they have the right to organize unions or like things like that? So it's like, are they exposed to like hazardous chemicals? Like what are their working conditions? And then for community, it could be health, it could be equity, it could be connectivity. For consumer, it could be consumer safety, number of things. So there is many. And then the way you collect the data for this, you have qualitative, quantitative, and semi-quantitative data. So sometimes like data like census findings could be one of them. And as engineers, we would often gravitate towards quantitative data as kind of the best data. But in social LCA, that doesn't have to be the case. I gave the example of like minimum wage versus living wage, livable wage. And let's say you can, in the company, if you're assessing the company, they can say, hey, we are not working, you know, more than 8 hours a day or whatever. But then if you interview people, or like company policy could be one thing, but then when you interview people, you will find out something very different. So these are just some examples. It's a very messy new methodology. And as I said, for pavements, we don't have that. Something that we have are environmental justice indicators, and you can find them on EPA's website. If you email me, I can send you some more resources. California has another one where you kind of assess neighborhoods that are hit with different types of environmental issues, such as smog, such as, you know, excessive heat waves, any local pollutants. So there are these things and these considerations, especially on the planning level. Pavement design, bidding level, usually you don't have these types of considerations, at least not yet.
Thank you.
We don't have questions online, so maybe we can go with Angela's question.
Mhm.
Hi, Milena. This is Angela Jamie. Thank you for the nice presentation. You mentioned the EPDs, and forgive me for my ignorance in this space, but you mentioned the EPDs are standardized. And I could see how, manufacturers would submit it per component. So if you're creating different mixtures, some with proprietary materials, how will an EPD at the mixture level change when inherently the components are changing?
Very good question. So to develop an EPD, you have a combination of foreground data and background data. And I'm gonna actually stop sharing my screen, and I knew it would be beneficial to leave it on. Let's see here. Yes. So here in this graph, I have a background data, which are the emissions associated with different components. So let's say cement. I know 1 ton of cement is usually 1 ton of CO2, give or take, etc. But then what is differentiating this process is the amount of cement that I have in the mix. That's my mix design. That's what I can influence. So far for most products, we have just one industry average environmental profile for cement, whereas, cement you can get in Illinois or I can get in Virginia could be very different cement. With that, there is definitely that question of like, hey, how accurate it is. So every 5 years, these rules for EPDs are updated again and again, and they tell you exactly how to run your LCA for EPD based on the latest industry standards. So I'll give you the example from concrete and concrete industry. There is, for now, let's say cement production, like this portion, very significant, as we saw from my results. It is only using industry average cement EPD. However, in the next iteration, I'm hoping that they will use product specific cement. So they will have not only differentiation based on cement amount, but also on type of cement that you're using. So every iteration, we are improving data granularity, we are improving data quality. So EPDs, even though they're standardized to the best data that we have, and data is constantly improving. I'm very happy to tell you, I've been working in this area for over 4 years now, and data has improved and much more data is available now compared to way back then. But one more thing I also want to mention is that EPDs are typically covering your conventional products. So it could be, let's say, paving concrete, self-consolidating concrete. However, let's say even ultra high performance concrete, I don't believe it's covered in EPD. Let's say geopolymers, like some out there researchy, very special mixes, very special products are not covered under EPD program, because often we don't know the ingredients, we don't know the components. So these would be your regular business practice, your bread and butter mixes. If you have something innovative, something crazy out there, EPD may not be the best tool. Then you would like to hire researchers to do an LCA and understand your product a little better. And I can give you one example. I was participating on aggregate PCR committee to update PCR for construction aggregates, and we were approached by several companies that produce carbon capturing aggregates, and they said, hey, can you include our carbon capturing aggregates into your EPD program? And our EPD program was for regular aggregates. We had steel slag aggregates, we had recycled concrete aggregates, we had a little bit of this and that, but not these absolutely new products that have never been seen on the market before. And we asked them, hey guys, can you tell us what is your process? How do you produce these aggregates? And they said, oh, sorry, it's a proprietary process. We cannot tell you. And of course, in that case, they cannot be the part of EPD, because EPD program is covering your regular bread and butter aggregates that you crush, sieve, wash, nothing fancy. So you don't have any of these other processes that are kind of emerging. So yes, EPD is definitely to that end good tool for your regular mixes, but not for very innovative products.
Thank you.
Thank you. So we may go with one last question quickly, which is an online question from Professor Al-Qadi. So I'll read it for you. Thank you for an excellent presentation, Milena. Is Federal Highway Administration working on CO2 capturing or storage? And he adds UIUC has a major program on this with Department of Energy, and cement is a major part of it.
Fantastic. Thank you so much, Dr. Al-Qadi. Good to see you here. So yes, there are several efforts. I do believe that we have the major, among federal government, the major efforts are coming from DOE. And that's kind of where they are putting the most funding and the most keen interest, because this is still innovative technology on the research level, whereas we have focused a little more on procurement and EPDs. However, we do have several noteworthy efforts that I want to mention. So first one is standardization on how carbon captured in different products, including cement, cementitious products, as well as these different aggregates that are just talked about. How that is being done and kind of the initiative towards improved standardization in that space, and that is a collaboration with NIST. There are also internal research projects in Turner Fairbank that are coming up on recycled concrete aggregate in their carbonation. And then we had a pilot study with Minnesota DOT where they have done carbon cured concrete. I know it's a little different technology, but it is being investigated on research level through several of these initiatives. So that's just something I want to mention. Again, DOE probably is the spearheading agency on that particular topic.